This is the village of Mandola. There is much excitement at the household of Dharampal, a local landowner. Sharma Sahib, the local policeman, has been called in early. This is because his house was burgled the night before. A lot of jewelry has been stolen. Sharma Sahib struts out, feeling important, pleased at all the excitement in this otherwise peaceful village. He also has an idea of who the thieves are. He suspects the local hoodlums, Ramu and Somu. Based on his suspicions, he brings Ramu and Somu to the local police station. But both insist that they were not involved in this crime in any way. Now Sharma Sahib very cleverly keeps his two suspects in two separate rooms. He tells each one separately, if you help me convict the other by testifying against him, you'll go scot-free. Interesting story, interesting dilemma. But what are Ramu and Somu going to do? Welcome to another episode of the Maths Factor, where we are going to explore game theory. This is basically the mathematics of decision making and is used extensively in economics. The Ramu Somu story is actually a classical problem called the prisoner's dilemma. And that's not all. We're going to explore how married couples, bickering neighbors and warring countries use mathematics in their decision making. Sounds intriguing. Keep watching to figure out how this works. Now back to Ramu and Somu. They are sitting in separate cells contemplating the choices that lie before them. Should they testify against the other or keep quiet? Now each choice has its consequences. Let's explore them. The first possibility is that Ramu agrees to testify, but Somu does not. In this case, Ramu gets off scot-free, while Somu gets a 5-year sentence. Similarly, if Somu testifies and Ramu stoically remains silent, then Somu goes scot-free and Ramu gets a 5-year sentence. If neither testifies against the other, choosing to remain silent, then both go scot-free. Sharma Sahib will have no reason to hold them. If both testify against each other, then they will both be forced to serve a 2-year sentence for the crime. The question, what will they choose? The problem in this scenario arises from the fact that each prisoner does not know what the other will do. Both will choose outcomes that will minimize the damage for themselves. So, the best outcome for both is for both individuals to remain quiet, as that would result in both going free. So that is the greater good for both, though not for poor Sharma Sahib. However, each is likely to choose the situation best for himself. Let's consider Somu. If he testifies, he'll get 2 years in jail or go free. If he stays silent, as he will either get 5 years in jail or go free. So the better option, though it may be less noble, is to testify. The same holds true for Ramu. Each will be hoping that the other guy remains silent while he testifies. While in reality, the most likely situation is that they both testify, spend 2 years in prison. Now, the prisoner's dilemma provides a great metaphor to understand the dynamics of competition and, more importantly, cooperation. It is often used to understand how competitors price products in a market, where both cooperation and competition can play a key role. The decision-making in many other spaces, like salary negotiations and auctions, can be phrased in terms of the prisoner's dilemma. Now let's take a step back and see what game theory is. Game theory is basically the science of strategy. What it tries to do is mathematically and logically work out the range of actions that players may take in order to secure the best outcomes for themselves in a wide array of games. The games vary, from chess to Cold Wars, from sports to child rearing. But the games all share the common feature of interdependence. Game theory evolved as a discipline quite recently. It was in 1944 that a duo of mathematicians, John von Neumann and Oscar Morgenstern, wrote a book called Theory of Games and Economic Behavior. Game theory received a lot of attention after this book, though the concept had been explored before. Now let's play another game called Public Good. We have a group of players. Each player has the initial sum of money and are given the option of contributing to a common pool. Now all the money that they contribute is then distributed between the players equally. Soon it becomes evident that not everyone has contributed equally to the pool. So what usually happens over the next couple of rounds is that the pool starts to decline. But somehow the amount almost never declines to zero. It means that there is always some hardcore givers who continue to put their money in the stash, no matter what everyone else does. Equally, there are the free riders who are happy to reap the benefit without contributing. An interesting fact, when the game is played anonymously, the contributing amounts drops drastically. Now, how does this translate in real life? Take taxes. Everyone benefits from public resources like roads, hospitals or parks. Even the free riders are tax evaders who don't contribute enough. On the other hand, we have contributors. Here's an interesting example. Take New York's Metropolitan Museum of Art. Admission to the museum is free. However, visitors are asked to make a donation of $20. Many pay. In fact, the museum collected over $29 million in 2009 through this donation. This giving is largely anonymous. However, it is clear that donations in other settings greatly increase with transparency. Acknowledging the donor helps boost donations. On this episode, focusing on game theory, we're all set to explore another game. This starts off with siblings, Shivang and Serena, quarreling. They have a cake that they need to share, and sharing this is no piece of cake. Shivang divides it. Serena accuses him of being unfair and taking the largest slice.
How is this fair? You have the bigger...
Now when Serena divides the cake, the same thing happens.
I'm going to tell Mom right now. I don't know what you did.
If a third party like a parent divides the cake, would that solve the issue? Not really. Shivang may still think that his piece has less currants and Serena may feel that her piece has too many walnuts. Then what is the solution to this never-ending quarrel? The answer is astonishingly simple. One person cuts the cake, but the other person gets to choose. The idea here is that the person cutting will be encouraged to make the pieces as equal as possible. And both the person who cuts and the person who chooses come out feeling that they've got a fair share. And so this game is called a fair division game. Notoriously, when the number of players increases to 3, things get more complicated. Let's take 3 children, Sanaya, Shivang and Serena. How will they divide the cake? First, Sanaya will cut the cake into 3 pieces that she thinks are of equal size. Serena verifies this process. If all the pieces seem the same, she does nothing. However, one seems bigger than the other one. She equalizes it by cutting off the excess and setting the leftover aside. Then Shivang gets to pick. Next, it's Serena's turn. If she has equalized a piece in the earlier step and Shivang has not picked that piece, then she needs to pick it. And the final piece goes to Sanaya. Now, if there was no equalization, the division is complete and the game is over. If not, between Shivang and Serena, whoever took the untrimmed piece, this case Shivang, cuts the leftover into thirds. Then each child picks one piece from the leftover, in this order. The one who took the trimmed piece, Sanaya. The one who cut the leftover. Complex, but fair. Cake cutting is a metaphor for any kind of fair division. It often helps in sharing of tangible assets like inheritance, as well as intangibles like time and effort. Let's move from the kids squabbling over cake to a slightly more serious conflict. Mrs. Mukherjee and Mrs. Khanna are neighbors. Mrs. Khanna always throws garbage on Mrs. Mukherjee's side. Mrs. Mukherjee keeps picking tulsi off Mrs. Khanna's plant. And Mrs. Mukherjee is constantly disturbed by the loud serials that Mrs. Khanna watches all the time. They decide to resolve their conflict over a game of tic-tac-toe. On day one, Mrs. Khanna starts off the game. They continue till one gets 3 in a row. In this case, Mrs. Khanna emerges victorious. On day 2, Mrs. Mukherjee starts off the game. And this time, she wins. She's jubilant. However, after a few days, things get complicated. Almost all the games end up in a draw. If they had studied strategy or game theory, they would have understood that once players get more experience, almost every game is likely to end in a draw. Now, a game like this is called a deterministic game. This means the outcome of the game can be determined right from the start of the game. What we can do with tic-tac-toe is actually plan the move in the structure known as game tree. This would be a graph starting off with the empty tic-tac-toe board with all possible first moves, second moves, so on, till all 9 moves are plotted. All very fascinating, but not much use to Mrs. Mukherjee and Mrs. Khanna, whose battle continues. Maybe they should switch to Ludo. Now, chess works quite like this. In spite of the complexity of the game, we can actually plot all outcomes. This property is what has helped develop computer programs that can play this game, like Deep Blue, the computer developed by IBM that in 1996 managed to beat the world champion Garry Kasparov. This marked the first time a computer was capable of defeating an expert chess player under normal tournament rules. Let's look at some bigger and broader ways in which game theory has been used in real-life situations. And one can't really get bigger than war. Let's travel back to the Cold War years when both the US and the Soviet Union used game theory to make decisions. And let's explore the context in which this worked. Post-World War II, the prospect of further communist expansion prompted the United States and 11 other Western nations to form the North Atlantic Treaty Organization, NATO, in 1949. The Soviet Union and its affiliated communist nations in Eastern Europe founded a rival alliance, the Warsaw Pact, in 1955. Now, this polarization provided the framework for the military standoff that continued throughout the Cold War. Now, the interaction between the two opposing sides, NATO and the Warsaw Pact, can be modelled as a variation of the prisoner's dilemma problem we looked at earlier in the episode. The best case scenario would be if both sides don't build a nuclear arsenal. It's both safer and more economical. If both sides build an arsenal, neither side has an advantage over the other. From each side's point of view, not building an arsenal as the other side builds one is the worst possible outcome, because it leads to strategic inferiority and potentially destruction. Now, the US used game theory in their decision making. They couldn't build an arsenal, so they started accumulating nuclear weapons. Without proper information from the USSR, they kept increasing their arsenal for fear that the USSR was increasing theirs. By 1953, both sides had nuclear ability. This situation gave rise to a doctrine called MAD. Not crazy. MAD is the acronym for Mutually Assured Destruction. It seemed given that both sides would use their nuclear ability for fear that the other would use it first. But in our matrix, there is another possibility: cooperation. If both sides are transparent, the level of nuclear armament does not need to increase. In fact, with transparency, both sides have in fact reduced their nuclear capacity. Let's now move from war to the story of John Nash, who was the inspiration behind the 2001 Oscar-winning film The Beautiful Mind. Nash received a BA and an MA in mathematics in 1948. He was then accepted into the mathematics program at Harvard, Princeton, Chicago, and Michigan. He felt that Harvard was the leading university, so he wanted to go there. But on the other hand, their offer to him was less generous than that of Princeton, so he went to Princeton. In 1950, at the age of 21, he wrote a paper where he developed the idea of the Nash equilibrium, a challenge to traditional game theory that would prove revolutionary to economics. But no one, however, recognized its importance at the time. After receiving his doctorate, Nash began teaching at MIT. In spite of all these achievements, he was frustrated by what he believed was the slow progress of his career and began to exhibit signs of mental imbalance. He claimed that aliens were sending him coded messages and that his picture was on the cover of Life disguised as the Pope. Nash was committed for a short time to McLean Hospital, where he was diagnosed with paranoid schizophrenia. For the next 20 years, Nash suffered from the disease until he slowly began to recover in the 1980s. In 1994, he received the Nobel Prize in Economics for his work in game theory, for the paper he wrote when he was 21, and resumed his work at Princeton University. Quite a dramatic life, and makes for a great story, especially with Russell Crowe as the lead. But we can't quite leave it at that without making an attempt to understand his famous Nash equilibrium. Let's look at an example to understand this. This is Ankit, and this is his wife Ambuja. Now Ankit and Ambuja have decided to have a special evening together. They've left their 2-year-old daughter with their grandparents and wanted to spend some time alone. Unfortunately, they're unable to decide what they want to do. Ambuja wants to head out for a run, while Ankit wants to eat chaat at the local restaurant. Sounds like a typical marital conflict, doesn't it? It's also a classic game theory experiment and is called the Battle of the Sexes. Now let's see how we can explore their choices. Let's map it out onto a matrix. We will assign the values to each of their choices. The option where he eats chaat and she goes for a run will get 0, 0. Similarly, if he goes for a run and she eats chaat, unlikely as that may be, we'll also get a 0, 0. This is because the most important thing for the couple is to actually be together. So, if they decide to each do something separate, mathematically, they will get almost no joy from the evening. Now, if they both go to eat chaat, the man gets a payoff, 2, since he gets to hang with his wife and eat chaat, while the woman gets a payoff, 1. She gets quality time with the husband, but no joy from the chaat. Similarly, if they both go for a run, then the woman gets a payoff of 2 and the man gets a payoff of 1. Simple enough, right? Now what Nash did was beautifully simple. He asked the following question: what strategies for each player would represent a steady state of the game? One in which neither player has an incentive to change given what the other is doing. Let's look at the options a little more closely. Let's see the option where both players have chosen to eat chaat. If Ankit sticks to eating chaat, then Ambuja would rather eat with him than move right on the grid, which means she goes for a run. And if Ambuja is eating chaat, then Ankit clearly doesn't want to move down and run alone. So in this particular choice, neither will move, presuming the other sticks to the choice. It is a Nash equilibrium. Let's see the running choice. If Ankit is going for a run, Ambuja is unlikely to shift to eating chaat. And if Ambuja is going for a run, then for this evening at least, Ankit has decided to prioritize being with her over eating chaat and will not shift. So yet another Nash equilibrium. The outcome in which each goes their separate way, Ambuja for a run and Ankit to eat chaat, is not an equilibrium. Here the woman would rather eat chaat since she will then get the pleasure of her husband's company. She gets little pleasure in running alone. So this is not a Nash equilibrium. The other corner where Ankit goes for a run and Ambuja to eat chaat is also not a Nash equilibrium. All quite fascinating, but we are running out of time today. It's quite evident that game theory plays a crucial role in our lives and provides startling insights into all endeavors in which humans cooperate or compete, and covers areas varying from biology and politics to agriculture and economics. Game theory has proven instrumental in helping us understand how and why we make decisions. And that's all for today.